great research. Again, I'm not going to make a long introduction, but just to say that as a theoretically inclined person who's not really a card-carrying member of the CS theory community, many of us are always looking and wondering, waiting for when the CS theory community does things that are particularly interesting and relevant to us. We learn about it kind of quickly, and we're always intrigued. And that happens from time to time, and often it happens the name Ravi Kannan is associated with it over the years. So I'm particularly eager to hear what he has to say about this topic, which I know he's actually been thinking about for quite some time. He's probably the one person in the CS theory community who's had big data in his mind, I think, for quite some time.
Okay. Thank you very much, Mike. I hope to live up to that introduction. So thank you for all of you staying and coming here for the workshop and sort of inaugurating this wonderful building and the institute, which all the folks here have worked very hard to bring, and I think I should give them a hand before I start even. Thank you. So my talk was, since it's the last talk, I'm supposed, also since I'm sort of grown up, I'm supposed to philosophize a bit. But, I find myself lacking what they call the vision thing. So mostly I'll just do vignettes from things I know, which connect up, as Mike said, which connect up these various areas, numerical analysis, machine learning, statistics, as well as what we've come to call TCS in the last few decades. Which is all, there's no clear boundaries, but we'll try to connect up the lot. So I call that, so since I don't have vision, I borrowed some. Here was a talk that Dick Karp gave on the 50th anniversary of Fox's talk, and he said, what makes an algorithm great? And I'll borrow this for saying what makes big data research great. Now the color coding is not his. I imposed my color coding on that. I just simplified. The blue was truth and beauty, if you will. The green was useful. The reason I put this up for big data in particular is we've heard a lot of mention of how useful things that we do in the paradigm of big data are. But I'd also like to stress that a lot of the techniques that people have developed and you've seen over the week or really do have the other component, truth and beauty as well. And we'll probably see a little bit of that.
Is there a color for the intersection of the two?
There's no, well, it's a wavelength. There's complete frequencies in between. Yeah, I suppose, it's really not a strict division. So the theme, the starting theme of the talk, and I'll have a couple of pictures on the theme, is that by now this is not even worth mentioning because you all know this, but geometry, that is viewing data as vectors, turns out to be very useful even in cases when there are no vectors in sight when you see the data, right? And randomness mixed in with linear algebra, that vectors give you linear algebra, randomness mixed in with that is extremely useful. Again, you've seen this over the week. Now, generally, quite often we view data as vectors, but it turns out also to be very useful, as people in optimization have done for decades now, to view solutions as vectors. So, for instance, if you want to solve a very large traveling salesman problem, what do? You represent the solution as a 0-1 vector in an ungodly number of dimensions, and then somehow it all works to solve several thousand city problems. Those are the champion solutions. But it views the solution as a vector. Now you can ask, is geometry just a bookkeeping device? And we'll see. We have seen already, we all know by now, but I'll show you some pictures, that it's not. So this should be the real title of the talk. Much of the material is also due to John Hopcroft. The way of viewing, we have finished writing a book which you can download. Please, it's several hundred pages. Please don't print it on a Calvin printer. You can download it and use it any way you like. Print it at home, but not here, right? So several of the things are from that. That's both an undergraduate and advanced undergraduate and graduate text that you're free to use. Okay, data as vectors. So again, this is by now more or less a given in a lot of people's mind, but let's quickly see some aspects before we go to some brass tracks. It's useful to think of it. The departure from traditional stuff is that, or physics if you will, is that these vectors reside in very high dimensions, right? Even if there's no obvious geometry to the data on the first sight. Now it's difficult to pin down, attribute this to one person or whatever, but it is the case that for us in this setting, in information retrieval setting, Salton thought of the vector space model, document term matrices, But there are lots of uses in economics and operations research and computer science before that. Of course, customer matrices, customer product matrices. Now, here is a more recent thing, Alon, Matthias, and Zaghetti, in viewing net flow data and trying to compute frequency moments. And again, this has been covered in the talks, so I won't go into detail, but they formulated this as a problem in a very high dimensional vector space and then projected it down to get its length, right? There was no vector there, it's just that's the way they formulated it. Feature vectors in machine learning are pretty standard. Now, you all know again, but I want to stress this with some pictures, that the vector notation is not a data structure just, it's more than that. All kinds of things like orthogonality and singular vectors have very nice meanings. Without going into detail, but I have a couple of nice pictures from past talks that I thought I would put up. Here's one use of orthogonality. If you represent web pages as vectors, let's say you put down whatever terms occur, each term is one component and you put down how many times it occurs or some function of it. If you search for the word Jaguar, it's now not the case, but it used to be that you would get mostly the cars. If you're interested in the animal, you're sunk. Now, we saw during this week that if you have a very large collection of vectors or a very large matrix, you sample rows of the matrix, or if you will, you sample some of the vectors and then process them. One sampling technique that you saw was using length squared sampling. That is, you sample with probability proportional to the squared length. Now, if you had 90% Jaguars and they were much longer, you'd never see the animal if you did this. How do you fix this? You saw in the talks a way of fixing this using leverage scores, but here's another simple geometric way of fixing this problem. Instead of picking single vectors with length squared probabilities, let me pick pairs of vectors with probability proportional to the area squared, it turns out. And this is, the square keeps appearing here. That's the truth and beauty component. If you didn't have the square, linear algebra would be in trouble, right? You wouldn't get as nice things. And in fact, here also you wouldn't get as nice results as you do with the square. With probability proportional to the squared area of the triangle spanned, that would favor picking one of these and one of these. Picking two orthogonal vectors or nearly orthogonal vectors, because then you get a large area. This is a technique that was used by Deshpande, Rademacher, and Mempala. It does many of the things that leverage scores do, but differently and with different bounds, right? Now, you could have a more serious problem, and this is mostly to thank my co-author, Alan Fries, from a long time. You could have what's called the Fries problem, or you could have even worse problems, but there are three meanings to the word Fries. The most important one is this. This is my co-author, right? But he may not have as many pages on the web as the magazine or the architectural style, and here you would want to pick triples of vectors with probability proportional to the square of this volume of the simplex they span. And that turns out to give you very nice theoretical results. Okay? This is called volume sampling. I won't tell you more about it, but this is all just to say that the vectors are there not just for being data structure, but for very useful things like this, geometric things.
Can I actually pick another pointer? There's a very nice recent work by Ben Taskar, University of Washington, on determinantal point processes.
Oh, okay, good.
That have exactly a volume interpretation and have a diversity interpretation, so zeta analysis, and have connections into the physics literature. It's very pretty. I'm sure it's...
Yeah, it's a good point. There's somebody called Manjunath Krishnapu, who was also Yuval Perez's student, who's also worked on. So the determinantal processes and volume sampling have been connected up now, and indeed, yeah. Yeah. Okay, so now randomness. Here, there's a slight distinction that I want to emphasize, as you all know again that this is true, but either the algorithm or the data can toss coins. What does it mean for the data to toss coins? You have a stochastic model of data, and clearly in statistics, things like mixture models have been long studied. In computer science, probably in TCS, Karp started in a way the probabilistic analysis of algorithms, on which there are very nice results starting from the 70s. That's when the data tosses coins, right? The other thing, randomized algorithms, is when the algorithm tosses coins. You have a random number generator built, which the algorithm can use. And I call this a well-kept secret weapon of TCS, not anymore. For a long time, it used to be in the sense, for instance, Valiant and Brebner had beautiful results on network routing using randomization, load balancing using randomization, and nearest neighbor, which you saw in this during this week, and you saw the results that Alex presented. Random projections are very useful for reducing the dimension. But in practice, these things are not used nearly as much as in theory. Even for the nearest neighbor, people use data-dependent projections. For instance, PCA, more so than random projections, whereas in theory, you use random projections. Network routing, again, people are sort of loath to use randomized routing tables for a good reason. But in any case, if this is not the case, it is a secret weapon anymore. It's now sort of come out in the open, and we saw quite a bit of that during the week. Okay, so now I come to the brass tacks, Bootcamp, singular value decomposition. Just in case you haven't heard about it, I'm sure all of you have. Half a slide description. Perhaps I want to say that maybe the perspective is, I should crack this little joke on statistics and machine learning. Why not, right? Statistics has for a century or so buried beautiful ideas in bad notation. And somehow machine learning seems to have inherited this. And I mean, I want to try to see if I can, I mean, this is not my idea, obviously. It's an old idea, but there are a lot of ideas in machine learning like that, which, you know, once you decipher the notation, you see how pretty they are, how nice they are. Anyway, SVD, hopefully without notation, I'll present it. There'll be no symbols on this slide. So I mean, there are n data points in D space, rows of a matrix, if you will. I want you to think of the SVD as just doing the following. It's finding the best fit subspace of each dimension, right? And best fit in the sense of squared perpendicular distance is minimized. Okay? This is not least squares fit where you minimize the vertical distance. You take the perpendicular distance to the subspace, square it, sum it over all the points, minimize it. That's SVD. Okay? Without symbols, right? And the most beautiful thing about truth and beauty of our SVD or linear algebra in general is this. I think of it as this fact as an algorithms person, which is a greedy algorithm works. What does it mean? If I want to find the best fit k-dimensional, 100-dimensional subspace, I can find the best fit first one-dimensional subspace, one line, find the best fit perpendicular to that, 100 times I'm done, right? That is a very nice fact, which you can prove, which is elementary proof. And that, I think, is, you know, underlies sort of the truth and beauty of it. Historical surprise. 20 years back, if you asked a TCS person, even like me or anybody, whether SVD would actually scale up to modern data and be useful, we would have been surprised that it could actually do that. But it certainly is one of the main tools now that has scaled up and has become very useful. And first reason is, of course, that we have decades of very good advances in numerical algorithms that have gone that are behind this. Then some of it is our well-kept secret. Again, we saw Petros and Mike Mahoney discuss this in detail over the week, that in fact linear algebra, randomized algorithms now play a role in numerical computation. So I don't want to discuss any of these that is known. I would like to focus a little bit more on, the numerical people have principal component analysis applications in mind. I want to show you some slightly different applications that have come up in the recent past. And in these applications, it's not sometimes the algorithms that's new, it's the fact that we can prove that they do certain things, that in some sense there are theorems behind them. Okay. Another fact to know is, one reason to do SVD, for instance, if you're doing nearest neighbor search, you reduce the dimension. The problem was sitting in a 1,000-dimensional space. Nearest neighbor costs you a lot of time. You reduce it to 100-dimensional space, you save time, efficiency. That's not the aspect I want to stress, because that's usually stressed aspect, and we've heard about it. But of course, there's another aspect, which is SVD can actually help, not just in efficiency, in actually getting the answer, which you otherwise wouldn't get. And I want to give you one or two striking examples of this, where SVD acts as if it's a denoiser, that what you throw away was as if it was noise. Not necessarily stochastic sense, but we'll see other senses in which it was a noise. Okay, here I'll start with the application of SVD, modern application of SVD, if you will. As I said, the algorithms here are not necessarily new. People use them as heuristics, but the point is that you can prove things now. So here's a standard object in statistics, mixtures of densities. You have k-spherical Gaussians, right, in D space, and it's best to think of k as a constant. K is mostly a constant in this talk. And you have a weighted sum of those. That's a mixture, right? And we'll see one picture in the next slide, but right now bear with me. So the idea is I'm given polynomially many samples from the mixture, and I would like you to learn the mixture. I'd like you to learn the components and the weights. Can you do that? Well, okay. So as always in statistics, right, you want to know how many standard deviations apart are the means. So if you have a mixture of several things and the means are sitting on top of each other, two Gaussians, there's no way you can tell one from the other, right? So you want a certain number of standard deviations separation. Standard deviation is the right unit. And indeed, we know, and this is a beautiful result of Impala and Wang, natural as it sounds, it didn't come without hiccups. This was several years of work and several papers, several authors. This is in a way a culmination. It says if the means are separated by a constant, maybe logs here, number of standard deviations, then in fact you can learn. You can learn the components. Okay. Now, again, it sounds natural that you say, yeah, sure, but it's not so sure. Here's a word of caution. Suppose I say I'm going to learn by saying that I take a data point, and take all its sort of close data points and consider them one cluster. Then you will be wrong unless the separation is much more than a constant number of standard deviations. You need d to the 1/4 standard deviations. Again, I'll show you a picture on the next slide, which perhaps is a nice picture to remember. It's a very simple picture. On this slide, I want to describe how SVD is used. And again, it's very pretty, and it takes only 4 lines. This is Impala and Wang. They argued, so here's the argument. Take one component Gaussian, it's a spherical Gaussian, and let's look for the best fit line. Best fit means least squares, right? Best fit line for that Gaussian. Let's assume the origin, the mean of the Gaussian is not the origin, it's sitting somewhere else. So here's a picture. Here's the Gaussian, spherical, and here's the origin. What's the best fit line? I claim, just sort of by staring at the picture, the best fit line is this. Best fit one-dimensional subspace, excuse me. Line going through the origin, one-dimensional subspace is this. You can play around a little bit and you'll see that that's true. I won't prove it, but it's very simple to see. So what? Now by symmetry, suppose I want the best 10-dimensional subspace. The least squares fit 10-dimensional subspace. I claim any 10-dimensional subspace containing this line does as well as any other, and those are the best. Okay? And that's a simple symmetry argument. Now I claim we have a big coup on our hands because of this. Why is that? So any k-dimensional subspace containing this line is the best for that Gaussian. That's true for every one of the Gaussians. And therefore, you take the space spanned by all those k lines, lines joining the origin to the means of each of those. That subspace is individually the best for each fi, so it must be the best for the weighted sum. Okay? Now, I can therefore find it because I know how to find SVD. I know how to find the best fit subspace. I find it, and that subspace now contains all the means, and I project all of the action to that. I've reduced a d-dimensional problem to a small dimensional problem, and I can solve it. Now, I could have projected to any space, a random space. That wouldn't do, because if I projected to a random space, the means could come closer, as much closer as the data points. And that's no good, because I'm measuring intermean separation in terms of standard deviation. If both fall by a factor, I'm not gained anything. But here, the intermean separation has not fallen, because I've gone to the space of centers, right? So, indeed, I can project, and then I can learn. Okay. Now, this was for a mixture of spherical Gaussians, but indeed, okay, so I should show you this picture first, but before that, indeed, let's now come to this interplay between TCS and statistics, if you will. So the k-means objective function is just minimize the sum of squared distances to cluster centers. So here I've shown you two Gaussians. The centers are here, sort of uncomfortably close, and these Gaussians have standard deviation 1 in each direction. They're sitting in d dimensions, so they'll be root d sigma away from the origin, from the centers, right? Okay. Now, the exact minimization of k-means is NP hard, so in TCS, we have spent quite a bit of effort, and in fact, it is a tour de force that now we have, maybe 10 years ago, as of 10 years ago, we have a constant factor approximation. That is, we can minimize the k-means objective function to a factor of 2, okay? Which was a big achievement. Now, I want to ask you, any takers for that? What will the statistician say? Well, the statistician says the following. Here, I have two spherical Gaussians in D space. D is large. The standard deviations are sigma in each direction, and the centers are 100 sigma apart. Okay? And you run your factor 2 approximation k-means algorithm. Is that going to do me any good? The answer is no, because the mean squared distance of the points is much higher than sigma squared. It's d times sigma squared. Every direction is sigma squared, d direction, so it's d times sigma squared. And the errors are of this order, d times sigma squared, which is no good because you're only allowed to make errors of the order of sigma squared if you were to distinguish this from that. So in fact, you could get most points wrong and still have your objective function a factor of 2 off. So, question, do we just throw away all these developments from TCS? The answer is obviously no, because otherwise I wouldn't be saying it. We'll see how to use that. So hopefully this picture is great. This is actually a simple, very nice picture to remember, right? Sometimes one mnemonic for this is the sun and the planets or what have you. Here's the sun. They are really very far compared to the separations you need here, right? It's extremely far. D is very large. D is in the thousands, let's say. So what do we do for this problem? So I'm going to now generalize this, the thing that Wempala and Wang did, which is project and cluster, to a model where there's no stochastic model. And so you have n points in RD. I want to cluster them into k clusters. Okay. And I don't assume a stochastic model. No Gaussians, right? We don't know that they're Gaussians. Now, I want to say that the main point of this slide is you should not look at the k-means objective function. You should look at a different objective function, namely the variance of the clustering. So what's the variance? Variance is what it should be. There's no stochastic model now, so how do you define variance? Well, you just define the max overall directions of the mean distance squared to the cluster center. So you take a direction v, unit vector, you take the data point to cluster center vector separating those two, take the square of the dot product, and I should have averaged that. That's a 1 over n. There are n data points. Now, I should have averaged this 1 over n. And it's easy to see that there's a spectral norm of a particular matrix. Don't bother if you didn't. This is the matrix of cluster centers. It's just a spectral norm. Okay. So I claim this is a better quantity to deal with than the mean squared distance. Certainly for the Gaussians it is, because the standard deviations were the right thing to do. But how about in general? Okay, so we ask, can we find a clustering with variance at most a constant factor of optimal? So every clustering has a variance, that's this quantity. I want to optimize that, I want to minimize that. Can I minimize it to a constant factor, like I did for k-means? Is the clustering I find like in that process any good? Okay, and then, so here's why we didn't like, here's why the last picture failed. This picture failed because I had a simple generative process of two Gaussians and my algorithm did not distinguish them, okay? Which I should be able to, which Wempala Wang, for instance, can, right? Now, can we fix that? And now, but I want to fix it more general. So, define an unambiguous clustering as a clustering where cluster centers are at least a few standard deviations apart. Again, it's just a standard mnemonic from statistics, means apart by 100 standard deviations, right? As we had in a stochastic model. Now, we don't have a stochastic model. We have variance without that. Is the clustering we find any good? So I would like to say, if there were those two Gaussians or any unambiguous model, I'll get it. Okay? Is that true? I'll nearly get it. I won't exactly get it. The answer to all of these is going to be yes, right? And the algorithm is going to be extremely simple and natural. And again, I want to emphasize that heuristically, people probably use such algorithms, but the point here is to prove that. Here's the algorithm, which is extremely simple again. You don't do your k-means in the big space. Instead, find the SVD subspace, which is the best fit k-dimensional subspace, if you're doing k-clustering. Project the points, and then do, indeed, now we will use the TCS developments, which is the two approximate k-means clustering in the projected space, but not in the whole space, in the projected space. Okay? So notice that projection saves me time because it's lower dimensional, but that's not the fact that I'm going to use. I'm going to use the fact that the projection does something which you do not accomplish if you do the clustering in the whole space. Namely, it fixes that problem, but more generally than just Gaussians. So this theorem is fairly simple, actually. It's not very difficult to prove. So if there is an unambiguous clustering, there's a clustering with the inter-center separation of at least a few standard deviations. Our clustering, this guy, there's one fix that you have to do, but this guy finds it. Finds it means only approximately a small fraction of points could be misclustered, could be differently clustered than unambiguous. So it finds the Gaussian case or any case when there's an unambiguous clustering. And in fact, it does minimize. This algorithm minimizes also the variance to a constant factor, which is another thing you wanted to do. The cluster centers found, here's an important point. The cluster centers found are within a few standard deviations of the true centers. Okay? So you had an optimal variance clustering, that's the true centers. These are within a few standard deviations. Now, it turns out, so k-means is one of the most frequently used algorithms, and one of the most frequently encountered problems is that the starting centers are no good. So an example, a very good example where you have three clusters. Like that, and if you start with three centers like this and you run k-means, you'll never get somebody there. You might get sort of, you'll move up somewhere there, but you won't get everything right. Is that the picture I wanted? Maybe the picture I wanted is 2 here and 1 there. But in any case, the start is very important. This gives you a way of starting with centers which are only a few standard deviations apart from the true centers. In fact, I don't of no other means of doing this. Recall the sun and planets picture. If you just pick data points for your start, which is standard, you'll be very far away. Every data point is really far away from the center, from its cluster center. So you can't just pick data points. And k-means plus plus are various heuristics. All of them have this problem that you're not guaranteed a good start. But this SVD does do that, right? As I said, these are not so difficult. In fact, a harder theorem, which we, with Amit Kumar and I, were able to prove maybe about 3 or 4 Foxes ago, is with this start, if you run the traditional Lloyd's algorithm that has exponential convergence, the distance to the true centers falls geometrically. Okay, that's a bit harder to prove. This says you get a good start doing this. Okay. So again, it's what you would very simply and naturally think of. The point of getting rid of the other dimensions was not just efficiency, but it helped you in a way that doing the whole thing doesn't. So it's sort of the other dimensions are somehow noise in this. I'm
missing something on that last slide. So this failed with some probability, or so it's not.
So here there is no probability. Where are you thinking there is?
Well, I'm just wondering. It's like you're not saying that you can solve the k-means problem in polynomial time here. So where
No. You're off. I mean, so you are not clustering epsilon fraction of the points right, for instance, right? So you don't get everybody right. And usual way to fix this, people make assumptions about the separation. Then you can get everybody right. Yeah. Sorry?
Will a similar approach work if the native process is not Gaussian?
Yes. So this theorem is for just arbitrary deterministic data, no Gaussians. Okay. But you're off by epsilon fraction. Now, there are assumptions, deterministic assumptions that fix that get everybody right, but they're assumptions, right? You don't expect to get everybody right without assumptions.
The assumption is that there's an unambiguous cluster.
Unambiguous only gives, so the trouble with unambiguous is you still could have a very small cluster that's far away and you won't get right. That's actually the problem here. Unambiguous is not enough. To get every point right, you have to assume that every point has a property which we call proximity, which is that it's actually A closer to its own center than any other center. This, you can have a small fraction which are sitting somewhere else and then you will be in trouble. Yeah, this works for deterministic data as well. Okay, that actually was the first topic, and I'm going to move to SVD and constraint satisfaction, unless there are other. Yes, sir.
What's the unambiguous assumption going to be? The assumption that Swami always has in their version, where they say, if you have this kind of collapsing cluster side where you kind of.
Okay, good question. So let's get in. So there have been notions of what's called stability, and for instance, Nati has worked on it for the max cut problem. Now, for the clustering problem, the stability assumptions have generally said my k means objective function, something about it being 1 plus epsilon off. And unfortunately, they failed for the two Gaussians. So the traditional assumptions of stability, or so the moral of this story is don't deal with the whole dimension. You must SVD, you must project, and they deal with that. So the what Swami et al. Did, and Avram Blum and Anupam Gupta and all have other notions of stability. They are all dealing with a big dimension, and they will fail the Gaussian example. So this is actually, in a way, some notion of stability, the last slide, was some notion of stability. It says that if your optimal clustering is stable, but you must measure it in standard deviations, not in the whole space. Otherwise, it won't work. Right? Then, in fact, you can find it. So another perhaps slightly, I'm picking examples of SVD use which you might not have seen before. That's what I'm doing. So constraint satisfaction problem, max cut, max k sat, max 3 sat, satisfy as many clauses as possible. We'll see that SVD can help us here. Okay. Let's look at max cut first. Max cut you can formulate simply as this, right? Aij is the adjacency matrix, if you will, or edge weights if you have edge weights. Xi is 1 if it's in the S part of the cut. It's 0 if it's in the S bar part. So S to S bar edges are counted here, right? And that's a quadratic form. I've written it in a way that perhaps linear algebra and SVD will be suggested. By this X transpose A 1 minus X, you must maximize over 0, 1 vectors. That's NP hard, of course. But suppose we have we find the best fit matrix SVD. We do K rank K fit, so that now this is spectral norm. When I don't have a subscript, I always mean spectral norm, which is the maximum singular value of this matrix. Suppose that's less than delta. Let's see how we can use that to solve the max cut problem. Now, instead of solving with edge weights A, let me solve with edge weights AK. So this is traditionally what you do in approximation. So here it's not actually denoising, but it's actually efficiency. So you project data down to the k-dimensional space and solve the problem with these edge weights. Now, since we have this little inequality here, so x and 1 minus x are vectors with norm root n, let's say 0, 1 vectors. Root n is the norm of each of them. So you get an n there. Right? But that's true for every x. So the error is at most delta times n overall. I'm not saying anything very significant here, but if I can solve it with AK instead of A, I'll be in good shape. Now, it's easy to argue that this delta is actually very small for certain matrices, in particular adjacency matrices of graphs. Delta is really this small for a small rank. So the rank depends only on epsilon, and delta is this small. That's a very simple argument. So if you did SVD, you would find this good an approximation. Now, it still remains for us to solve the problem with AK, right? This AK problem has to be solved. But why is that going to be easy? So if K is small, K is constant, I have a constant rank matrix, which is the edge weights. And somehow, before you look at this, somehow I used to have a full rank, perhaps n rank matrix, and I have an n dimensional problem, n degrees of freedom. And I've come down to k degrees of freedom. K is constant. Now the general model to think of if you have k degrees of freedom, you can always do the problem in exponential only in k. And in fact, that's true. I won't argue that in full, But let's pretend that we had a very special k equals 1, and our matrix of edge weights actually looked like this, UU transpose. It was symmetric, right? Then what do we have to do? We have to do this maximization problem, ui uj xi 1 minus xj, summed over all ij, no graph now, all ij. And that's just actually, you think about it for a minute, you see that that's just splitting the indices up so that the u's sum is about the same in the two parts. You do best if the sum of the u's in the one part is half the whole. Okay? And you can do that by dynamic programming. That's just a set approximate. It's all approximate by dynamic programming. And indeed, for general k also you can do by dynamic programming. So in this sense, somehow, you know, it combines what is a traditional TCS tool dynamic programming with SVD, right? So to do this problem. Now it turns out it's not just max cut. You can do all max 2 CSP problems this way, only to a certain error. I mean, the error is always there. Okay, so maybe I should. I'm going faster than expected. Are there any questions to stop me?
Let's
Yeah.
go back to the last one. So you have to solve subset sum. I don't understand. So you all have to do it exactly? Is that the idea? You're just
No, the AK also we do approximately because we are anyway making an error in the other part.
Okay. And so you could solve subset. So what's the guarantee on subset sum if you want to
Anything
get
you want.
Yeah.
that you just truncate.
Yes, you truncate.
You truncate and then
Truncate them, yeah.
Okay, I understand.
You truncate the beds and do it, yeah, for instance, yeah. And rank k is not very dissimilar. It's similar to that.
Okay.
Rank k is constant, and you're still making an error.
Case. Yeah.
Yeah. Now it turns out, maybe I don't know whether I said that, but it turns out it solves not only this kind of. It actually solves problems where the weights are metric. So here I say that, right? So it turns out matrices which are made of this requires a little. I won't show this, but if you have a matrix, just means triangle inequality. If triangle inequality is satisfied, then the matrix has a very good low rank approximation, but after scaling, you have to scale the rows.
And what's the
Sorry, what
approximation?
do you say? What's the statement? Sorry.
The,
Go ahead.
What's the statement?
The statement is, so suppose I have a max cut, suppose I have a max cut problem with edge weight satisfying triangle inequality, then you can get a relative error epsilon approximation algorithm by doing this in polynomial time.
So what kind of, what is the, did you quote a result for rank K approximation of metrics?
I didn't quote, but it's proved in that paper that, so roughly it is saying the following, right? That I can scale the rows. It's not true that I just approximate the original matrix. It won't do well. I have to scale the rows. And after I scale, the constant rank approximation is very good.
I see.
And therefore, it's enough to solve that.
Okay.
So all metric 2 CSPs can be solved to relative error by doing this process.
So it might be worth just as a comment to say that this is basically giving relative error for dense graphs only.
This is also giving relative error for dense graphs. Yeah. So it's giving relative error for dense as well as metric problems. And there's a common generalization of that. Maybe I'll write that. So if you have a matrix A such that sum over ij, aij. Oh, should I venture this because I forgot what it is, isn't it? Dij. I have to refer to the paper. It's been a while, but let me write this. Venture and write this. So let's see. For dense matrices, I take the degree of I, degree of j. Most of the well, I'm allowed to put di plus the average degree, dj plus the average degree. Average degrees are n. This gets you n squared. Well, yeah. So I think this is right. And it turns out triangle inequalities, metrics satisfy this, and dense graphs also satisfy this. It takes a couple of lines of proof to show that metrics satisfy this, and dense graphs also satisfy it. That's easier. You can do all that. It'll be exponential in k, yes. So yes, so it'll be exponential 1 over epsilon. But we don't expect to do in polynomial time in epsilon for all epsilon, right? Yeah. So it'll be exponential epsilon.
So just checking, you get n to the 1 over epsilon squared.
That's right. Not to the 1 over epsilon squared. There's been some work on improving the complexity of this, but I don't know exactly where it stands. In fact, I should mention that just as of the last week's workshop, a CMU student whose name I forget, now they can do the same thing by going up the Lazare hierarchy. But it doesn't yet do new things, and they're trying to do that. So it's a completely different technique for doing this.
James Lee?
No, I don't know. Well, I mean, I think they're still trying the general law. Okay, so in fact, it turns out you can do all this for tensors, and that is perhaps relatively new. Well, I mean, maybe new to some extent, so I'll describe that in detail. It's not that new, actually. It's a somewhat oldish paper by now, but maybe you have not heard about it, so I thought I'd get a chance to just talk about that. Okay, so let's, for this talk, only think of 3 tensors, although this whole thing generalizes to R tensors. Things are exponential in R, the arity of the tensor. So 3 tensors are just arrays with 3 indices, right? N by N by N arrays. Okay. A rank 1 3 tensor is the outer product of 3 vectors x, y, and z, and that has entries xi, yj, zk. Let's call that rank 1. The first lemma, which is not difficult to prove, is that, so max 3 set, or max 3 CSP in fact, but max 3 set is a problem of maximizing the number of 3 clauses that can be satisfied simultaneously, right? And that can be reduced, that can be written in this way, aijk xi, and this second coordinate could be 1 minus xj, and the third coordinate also could be either xk or 1 minus xk. There are 8 possibilities here. Okay? So it's a cubic form, right? Degree 3. And I'm going to represent, I'm going to talk of that as A operating on x1 minus xx over 0, 1 vectors. So it can be formulated this way. That again is not so difficult. The second lemma is also not difficult, but the third thing is a theorem, and that's more difficult. So for any tensor A, there are 1 over epsilon squared rank 1 tensors whose sum has the following property, is a good approximation to A. Now we have to be very careful. The approximation is in spectral norm, but the error is in Frobenius norm. Neither norm can be changed. So you would do much better if I could put Frobenius norm there, cannot. I'd do better if I also put spectral norm there, cannot. Okay? I have to do this.
What's the eigenvalue of a tensor?
So the spectral norm is the maximum okay, oh, I should write that. Thank you. Max over all unit length vectors, multilinear form, I'll allow. Sum over ijk, aijk, xi, yj, zk. Just spectral norm, right? So this lemma is quite easy. You just, in fact, you can just peel off rank 1. If this is not true, then you can peel off a rank 1 tensor with high spectral norm and keep repeating that. That's all. So that lemma is easy. But here comes the interesting part. This is hard. So, in fact, we can find in polynomial time, but it's exponential in 1 over epsilon. You can find in polynomial time 4 times that many, I think this should be just 1 over epsilon squared, 4 times that many rank 1 tensors whose sum satisfies exactly what we want, constructively, right? So again, spectral norm, Frobenius norm. Otherwise we can't do it. And at the heart of this, now this is like your greedy, right? For the SVD, what did we do? We peeled off the top rank 1 component and then repeated it. Greedy worked, right? We'll do the same greedy, but to do the greedy, we have to do this crucial step, which is I'm given a tensor, 3 tensor here, but it could be any arity. I want to find a set of vectors x, y, z, unit length vectors, so that they approximately give you spectral norm, but I'm now allowed an error with respect to the Frobenius norm. Again, we don't know how to beat that. Okay? Turns out we can do that for any matrix. Okay, so I'll show you one slide on how we can do it, but we can do that for any matrix, any tensor.
Is it NP hard if you want to do that with the spectral norm?
Okay, so I'm not completely certain of the current status of that. I believe it's NP hard for 4 tensors onwards, if you want to do it exactly. Now, for 3 tensors, there was some issue whether it's true or false, but I suspect it's still NP hard even for 3 to do it exactly.
To do tensor rank is hard.
Is hard. Hastad has some. It's NP hard for 3 also. Okay, good.
There were also papers about, so I remember who the people are, but I don't remember the exact, the general message was that there is no really good notion of SVD in dimension 3 and
So there are several impossibility results that even some definitions of them go all right.
The question doesn't even quite make sense.
Right.
Yeah. So I'm charting a path where, you know, I can prove something. But it's true that there are a lot of things that don't quite work, and there are actually some very nice recent papers of Moses Chareker and others. Okay, so I want, oh sorry, there was a question.
Are they randomized?
Yeah, this algorithm will be randomized.
So do we know how to do the same thing statistically?
Actually, I don't know. There are several questions with this that I don't know the answer to. I mean, as I said, this is, maybe our result is even 10 years old, but in some sense, there are several questions and improvements that would be very nice to have, but I don't know. But I want to stress that the point is you have to do it for any matrix A, right? Any tensor A, so it's the worst case in some sense. And epsilon isn't the exponent, which is a bad thing, but. Okay, so here is the description. Okay, so using that, it turns out that we can do relative error epsilon approximation to max R CSP problems for dense as well as something we call core dense for want of another word, which is a generalization of this sort of thing for tensors. This is for matrices and that's for tensors. But that I probably won't. It's more than, it's a metric sort of special case. So for instance, powers of metrics are also covered by it. That also covers powers of metrics. But I think, so actually a good question is, does it cover anything else interesting? I don't know. Other interesting things that it might cover. The conditions are sort of like that, but I don't know what else it covers. What are the classes? Okay, so one slide description of this algorithm. So norm maximization for tensors, spectral norm maximization, approximate, of course, right? We want to find unit length vectors, maximizing that. So, observe, the first one is just an observation. If we knew the optimizing y and z, right, then the optimizing x is easy to find. Why? I plug that y and z, and I just get a vector. And then it's just a dot product with x. It's simple, right? There's some kind of MATLAB notation, so it's some dot product with x. So then I can do that. That's not a problem. So I've reduced the problem to 2/3 this problem, right? I mean, 2 of the 3 have to be found. Okay, now observe that. Okay, so if I knew y and z, this would have been the optimizing x. So this is the guy I want to find. Let's write this out. This is the sum over all j and k of aj, k, yj, zk. I want to know the sum for my candidate y and z, right? For my optimizing y and z. But the sum can be estimated if I have just a few terms. Okay? You have to worry about the variance, but you can estimate it by knowing a few terms. But I don't know any terms of y and z. Let's lay that aside for a minute. But we want to know how do we make sure that the variance is not too high since the entries are all disparate. First, let's worry about that. If I knew the optimizing y and z, and I want to estimate this instead of writing this out, then how do I make the variance small? Now it turns out, and this of course I will not prove it, it turns out that it is sufficient to pick coordinates for y and z according to the squared length of the entire flat of the tensor that you see. That requires proof. That reduces the variance. You can prove a variance bound. So now I picked just a few j and k samples, and it's enough to estimate the sum by those j and k. I still don't know the yj, yk. But there are just a few j and k, so I enumerate all possible values of y and z to the granularity. So let's say I have 10 j's and 10 k's. So I have to know 10 values of y, 10 values of z, but I just enumerate them because there are only 10, right? I can do that. Then, so this gives us many candidate x's. So each candidate y and z gives you a candidate x. How do I know which is the best? Well, now I'm going to turn the problem on its head. So if I knew y and z, I can find the best z. Now I say, I have several candidate x's. If I know x, can I find the best y and z? Indeed, I can. That's a singular value problem, right? Because I plug in x into this expression, then what I'm left with is a matrix problem. It's one dimension less. It's just a top singular value of a matrix, and I know how to compute that. In general, if I'm solving an R tensor problem, in the bowels of it, I have to solve many R minus 1 tensor problems for every candidate. And then I take the best.
Can you explain step 3 again? The length squared.
Yeah, so see, I'm wanting to estimate the sum by picking a few j's and k's only. And somehow I have to get the variance of that estimate to be low for every possible value of y and z. All I know is that they're unit vectors. Okay. And it turns out that if I pick j and k with probabilities proportional to the squared sum of squares of all the entries in that j is one flat, gives you a matrix. In that matrix, I take the Frobenius norm squared and sample according to that. Again, square is important. Then I will get a variance, which is not very big. So I should say that this kind of technique called exhaustive enumeration really goes back to a very nice paper of Aurora, Karp, and Karpinski, maybe 15, 16 years ago, in which they used that to solve some similar problems like this. And since been used, well, I've used it in many papers, but it's since been used. So the point here is what? That you need only to estimate that, and then once you realize that, you sample j and k, and then you don't even need to know the y and z. You just enumerate all of them. Okay. So that actually more or less concludes my SVD and tensor stuff. Actually, there were some questions here. For tensors, it'll be nice to know. So there are a lot of theorems known. This train of thing I'm thinking of is something where you can prove that you can do a good approximation for every tensor. This is what I'm interested in. So in that, it'll be nice to know other theorems, better theorems, improved versions, other ideas. It'll be very nice to know. We do know a lot of impossibility results, a lot of those kinds of things. But okay, the last vignette is something completely different. I just threw this up. As part of writing the book, we had to put in Chernoff bounds, and here we come up with an interesting issue. This is not research as much as sort of pedagogical note, maybe. I can run over this, unless there are questions. Maybe I should pause for, what is the number of seconds? Somebody's 6, okay. Well, let's look at the clock. Any questions on? I should have a loud count and a bang or something like that. Okay, good. So let's.
So I guess I'll ask.
Yeah.
There's a whole bunch of linear algebra techniques to maximize these forms. Those don't work because you can't bound the runtime.
See, what I don't. So, for instance, you could say that you could do something iterative. I have an x, and I do the singular value find of y and z, and I put them in, and then I could do that. What I don't know is a proof that any of those yields you a good result for every matrix. Here's the error bound for every matrix, which is what I want, right? Somehow. So, for instance, one obvious algorithm to do this is you have an candidate x, you maximize to find the y and z. Repeat.
So, what is the guarantee
here? So you are off. Did I put? Yeah, the error is epsilon tensor Frobenius norm of the matrix A, which is bad, of course. It's higher than spectral norm, but that's.
And we don't know any lower bounds, right?
I don't know any lower bounds. So in other words, you can ask, what's NP hard for approximation? I don't know. That'd also be a nice question to solve.
The question. Sorry, what was the question? The question is.
The question was.
At what level can you actually approximate this eigenvalue, this norm?
Yeah. What is hard and so if you allowed an error of epsilon times Frobenius norm, this can do it. But can you do better, or what's hard?
I just saw a paper that was this hypercontractivity paper. I thought they had a lower bound for.
Well, how well you can do.
How well you can do that.
It must be hard to do relative error epsilon for spectral norm. I would think, but I don't know. No, for matrices, I mean, you can do it in polynomial time. NP hardness I'm talking about, right? Or, well, spectral norm you can do it exactly, right, for matrices.
No, I'm talking about rank 3.
Tensor, 3 tensor, yeah. You think it's hard, spectral norm with relative error epsilon, NP hard. I don't know for sure, but could be. Those could be interesting issues. Okay, so I think I'll just flash this maybe. Okay, so don't worry about the symbols here, but if you're teaching Chernoff, it goes like this, right? You have IID, mean 0, variance at most sigma squared, and slightly different from the usual statement, then, but absolutely bounded by 1. I put in red because I don't like that. You'll see in a minute why. Then you get tail bounds, which are sub-Gaussian up to a certain point. Beyond that, they are not sub-Gaussian. Okay? So I don't care about the constants here for the moment. Okay? But if you're teaching a course, very soon you have to prove a similar result when the xi are Gaussian. For instance, if you're proving Johnson-Lendon-Strauss, you have to prove this when they're Gaussian. Of course, this goes out of the window because you don't have absolute bounds, right? And you sometimes have to do it for Poisson exponentially and so on and so forth. The moment generating function exists, but only for certain lambdas, they don't exist. But here is a theorem which is true, which applies to all of these situations, right? And I presume it's folklore, but the proof is not very difficult. It does involve a little combinatorics. Okay, so you can replace the absolute bound by moments. Now, the point is, the moments can grow as s factorial, but not sigma to the s. It's only sigma squared. So Chernoff, I mean, Bernoulli random variables the moment bounds don't fall as sigma to the s. They only fall as sigma squared, because they really have heavy tails. So it turns out that that is true, and that gives you all of these bounds, right? I don't know why I put this up, because I was just working on this the last few days, but
follow from Kinshin?
It probably does. Well, usually you need more than finite moments, but maybe it does follow. I mean, it should follow from something more sophisticated, but I want like a half-page proof, right? Probably follows from the pairs. I mean, the exchangeable. I mean, certainly would follow from something like that. Okay, so that's all actually the talk, but there's one sort of open problem that I wanted to state, which I didn't put up on the slides. So all these randomized algorithms for linear algebra, right, prove results when the sample size is small. Now, I'm going to say constant, but you can do a little better. But what would be nice to prove is you take a matrix, you pick some rows, but you sample without replacement. Well, let's say you sample a constant fraction of the rows. Right. This is an old problem that we are worried about. In practice, is what you might do, right? You will have 100,000 row matrix. You don't want to sample only 100 rows out of it. You want to sample maybe 5,000. So you don't have very good results for that range. That, I think, would be a good challenge to, I mean, sort of big challenge to tackle.
In what sense are there not good results?
Well, for example, one thing is that the results we have, or Petros and Mike and all have more recently, all of those results, right? When the number of sample rows tends to n, you want the error to be going to 0.
The problem is we don't know how to analyze anything with the sampling space without the case. All the data is not fixed.
Yeah, so that would be a problem to tackle.
It's just that the concentration theorems, I mean, there are concentrations for without replacement. Those are, who do you use? Oh, those are well known.
Yeah, I mean the Höfting type of. I mean,
all the Höfting
yeah,
for without replacement.
yeah,
There's
yeah.
one that yeah.
So
Joel's paper, our paper has.
So, but Mike, they proved that sampling, what is it? Höfting's usual inequality, sampling without replacement, is no worse than the other one, right?
Yeah.
But the other one will end up requiring, this 1 over epsilon squared sort of kills you because it tells you have to pick n squared samples to get the error to 0, which you want n. I mean, right. you want to say that I pick 0.8 n, I get a good.
So you want to say it does strictly better?
Yeah.
We know how to do uniform sampling.
So the application of without replacement to with replacement may be off by a square. I mean, that's kind of question. So I don't have another half an hour's worth of material, so somebody needs to talk. Who would want to talk there? So let's see, if nobody has questions now, I can start pointing to people and say, do you have a question? Or we can go home early, it's all right too.
We can go get beer too.
It's not a bad thing to do.
Happy hour.
So when our first workshop is in 10? Huh?
Yeah, so we next week there is a lunchtime meeting where there's already 2 speakers lined up, and there was an
good.
this afternoon.
Okay.
And that's the only formal activity that I'm aware of next week.
And then the week after we have the workshop.
We're picking up on what we left off here. And Alice, is there anything else that we should know about?
Well, next week there's
there is the bootcamp.
Real analysis.
Real analysis bootcamp.
Haven't had enough already.
No, we are going to fit in through all those talks.
So the workshop in the week after next is at, it's not in here because so many people wanted to come. So we had to move it out to International House, which is 5 minutes walk.
We can drink there as we, no. No, I mean, as we attend to the talk.
You can do whatever you can try.
Okay.
You're on video right
Oh, I didn't know. This is being streamed and so on.
Without the context.
So you done?
Yeah, I think I'm done. I mean, I don't think there are any more.